Hi everyone, welcome to the next video. So what I'm going to do is solve the next type of problem, which is called an inelastic collision. So here we have two blocks, and you can see we have one that's moving toward the second block. So M1 is moving at 29 meters per second, and this one's at rest. And what makes this an inelastic collision is the fact that afterward they both stick together and move together. In fact, it physically says that in the problem, the blocks stick together after the collision. So we're going to answer the following questions. So I actually put this already on my sheet. There we go. Like that. You grab this. Okay, so here we go. So in this question, we have a couple things to address. So the first one says, which of the following quantities, if any, are conserved during the collision? I'm going to actually officially answer the energy question, but I know that momentum will be conserved strictly because there's no outside force in this problem. We don't see someone giving a force on this system or taking away energy, so we have a conservation of energy because no force external right here. And then next, I'm making a bold statement. I'll verify this, but there's going to be no, so I'll just say it like this. I won't say no, I'll say there is, there we go, there's my back button. So energy is not conserved. But I'll verify this, okay? So we're going to find the initial momentum of the system, the final velocity of the two blocks, and then the change of kinetic energy during this collision. I was just looking, I thought there was another question. Okay, that's fine. Alright, so let's move on. So let's start with part one. So what's the initial momentum of this system? So if it's asking for that, it's really asking for the total initial momentum, which would be block 1 and its initial velocity plus the momentum of block 2. Now block 1's going to have a mass of 1.10 kilograms times its initial velocity, which is 29 meters per second, like that. And then we're going to add the momentum of the second block. So the mass is 21.0 kilograms times 0. And the 0 comes from the fact that the block was originally at rest here, so V is 0. Now a shortcut is to, of course, ignore this term because there's no velocity, but let's just be complete and carry it out. So the total initial momentum of the system will essentially just be this calculation. Let me just grab my calculator. There we go. 1.10 times 29. So what I get here is 31.9, and this is in kilograms meters per second, like that. So that's question 1, the initial momentum of the system. What is the final velocity of the two after they collide? So I'm going to try to keep the two of them in the question right here. Move this out of the way. But if you notice this, I can write the equation that defines the system as such. So the initial momentum of the system has to equal the momentum final of our system. So the initial momentum we already did in part 1, but I'm going to write it out just to be complete. So this is the initial momentum of the system. Now the final momentum is going to be written like this. The two masses move together, so we have to add their masses. And then the velocity that they both move together are called VF final. So we put the F there to say that it's final, or the final case like that. So I'm going to go ahead and solve this out to find V. So we actually know this first part already. We calculated it. So I'm going to go ahead and use that shortcut because this is the initial momentum of the system. So 31.9 kilograms meters per second equals M1, which is 1.1, plus M2, which is 21.0. And then we'll go ahead and solve for VF. So 1.10 plus 21.0 gives me the following numbers. So I get 31.9 kilograms meters per second is equal to 22.1 kilograms times VF. 31.9, 22.1. So our speed is 1.44 meters per second, and notice that it's positive, so this is moving in the forward direction, which is right. So it's always good to think about the direction of these things right here. So let's go ahead and look at it up there. That makes sense. So we found the final velocity of the system. Now let's find the change of kinetic energy. So I know that we're going to have actually a pretty big loss of energy due to the fact that we have an inelastic collision, and that's a characteristic of inelastic collisions. But let's pretend we don't know what's going to happen. I'm actually going to solve this slightly different than I did before, just to show you that there is another method. So what you can do is you can find the total kinetic energy initial and then kind of compare it to the total final energy, like this. So let's go ahead and write our expression. So notice that we have two separate objects, so we'll have two separate kinetic energies. So let's go ahead and write that out. 1/2 m1 v1I squared plus 1/2 m2 v2I squared. Just like that. And then the energy of this block right here, it's going to be a model of the two objects. So it's actually going to be the two masses. So it's a little different, but it's still kinetic energy. 1/2 the mass, which becomes combined, v final, squared. So a shortcut is that I know that the velocity initial of the second block is 0, so that makes things just a little easier. So then we can go down to this. So 1/2 mass of the first object, 1.10, times its velocity, which was, I don't remember the velocity, it was large, 29. 29 meters per second, like that, is equal to 1/2 m1. So m1 is going to be 1.10 plus m2, 21.0, times the final velocity, 1.44 meters per second squared. Okay, let's find out our energy. So 1/2 times 1.1 times 29 squared. So our initial energy of the system was 62.6 joules, if I round. 0.5 times 1.1 plus 21 times 1.44 squared. I get 22.91 joules, like that. So this is an equal sign. So hopefully you recognize that these numbers are not equal. Which means kinetic energy is not conserved. In fact, let's just find the change in kinetic energy just to see it. So KEF minus KEI would be KEF, which is this, 22.91 joules, minus 462.6 joules. I get negative 439.69 joules loss. So again, the negative sign makes sense because we're going from, this is final minus initial, so we started off with more energy and we have left over, we don't have as much left over, so this is actually a substantial loss. So notice that's way bigger than what we calculated before. So yes, there is energy loss in this. So what is the change in kinetic energy? Negative 439.69 joules of energy lost in this problem. And that's again a characteristic of inelastic collisions, because when you collide, you're going to heat up those objects and a lot of energy goes into doing that. So that concludes the video for this problem.